All right, so today we're going to start looking at the tangent problem. And this is one of those problems that I said, this is what calculus really revolves. One of the big problems that it works through is this tangent problem. So we're going to kind of introduce it today. And within that, we're going to talk about average velocity and instantaneous velocity. We're going to build up to the difference quotient and finding the slope of the tangent line, and you'll kind of see how this ties together. Don't get in a hurry to skip through this first part. We're really building up an understanding here, so it's important that you kind of see that building happen. Your notes aren't going to start right away. I've kind of done some lead in here that you don't have for your notes. That doesn't mean you need to skip it or get to skip it. Still watch the video, and then I'll notate when the notes will start and you need to start writing things down. So let's throw an example out there. Let's say you're going to go on a road trip with grandma. All right. So pretty much here's kind of the path that we're going. Like this is just you're in your car, and as time passes, the distance you are from home is increasing. Just nice linear pattern here. Now, I like to start introducing some nice calculus kind of notation. This is a triangle, a Greek letter that is delta, and delta means the change in. So this is like when you're finding the slope of a line, you're looking in the change in y over the change in x. So to you, that means y minus y over x minus x, which is what I'm doing with these 2 points, math it out, and I end up with a 50. Now, if the slope is 50, what does that really mean for my trip with grandma? Well, remember that it's the y's over the x's, and the y's are measured in miles, and the x's are measured in hours. So when we write 50, what we're really writing is 50 miles per hour is what that means. The slope is the rate of change, and so it's how quickly you're changing or what your speed, or in this case, velocity is. All right, so here's the reality though. If you've ever been on a trip with grandma, probably it's going to go a little bit more like this. It's not straight shot. It's grandma driving at 50 miles an hour. Here we go. And at some point here, you're like, hey, grandma, mind if I drive? And so then you start driving, and you can see then that this rate is increasing, which means you're driving faster than grandma. But then grandma needs a break. And so we stop and have lunch at Hardee's on the turnpike or whatever. And you can see time is passing, but our distance from home is not. And then grandma says, hey, I think Dolores lives in that town back there, doesn't she? Let's go visit her. So now your distance from home is backtracking and you're losing time, but Dolores wasn't home and now you're kind of irritated. So now you're really speeding. Okay, so that's really what calculus starts to deal with, are these variations. Not everything's a nice, pretty linear function. And of course, we've started to introduce situations that have that variation, that it's not always linear. We know that, but calculus digs in a little deeper with it. And calculus also doesn't look at everything like it's all choppy and linear. It looks at curving situations. Not everything is so cut and dried. And so that's what you'll see a lot more of in calculus. Now, since we're talking slope, and slope we've recognized is really our speed. So we had mathematicians such as Galileo who studied motion a lot. Think of the motion of the stars. He was a big part of that, studying that. But he was in search of instantaneous velocity. So that's what we're going to work on today, is finding instantaneous velocity. Okay, so now your notes are starting. So let's look at this. This is our trip with grandma. Now, the speed is changing. All right. Well, I guess it's different than we're going to call it our trip with grandma. So you can see where the speed would change. And so if I want to find the speed, well, since it's changing over time, I sort of just have to pick a couple spots to work with. So that's what I've done. I've chosen from here to here. And I can see here that the speed was slower and then it got faster. And I'm just going to look for, okay, from here to here, what is that average speed? So to do that, I turn it into a linear situation and find that slope. So let's try that. this ordered pair, now I'm trying to totally ignore, in fact, in your notes, I think I've blotted out these numbers. Ignore these numbers down here. They're not there, okay? So I've just randomly picked this point and I call it X and Y, but I'm being fancy here with my F of X instead of writing a Y, but that's what that ordered pair is. So now I've chosen another ordered pair a little bit farther down the line, time-wise, and again, ignoring numbers, I'm trying to figure out what this X value would be right here. I don't know what it is, but I do know that I'm going to call this distance here from when I started to when I ended, I'm going to call that distance H. So if that distance is H, what do you feel like this X value should be? All right, I feel like it should be X plus H because I'm at this spot, but then I went over H more. So it's X plus H is that X value, which means the Y value is no longer F of X, it's now F of X plus H. Okay, now what I'm going to do is with these two ordered pairs, I'm going to find the slope of the secant line. So just doing my slope formula, I'm going to do y minus y. So that's f of x plus h minus f of x over x minus x. That would be x plus h minus x. And then I'm just going to kind of simplify it up. And you can see here that in the denominator, these two x's are going to cancel for me. The h is still going to be there. And this stuff up on top, it doesn't really reduce either. So my slope formula really is f of x plus h minus f of x all over h. And that is what we would put in for the slope of our, I used a term here you maybe don't remember from geometry, but a secant line, okay, so a little flashback to geometry so we have this figured out. Do you remember that in a circle, don't put this in your notes, okay, so in a circle, you might have a radius, you might have a diameter, you might have a chord. A chord is a segment that hits the circle in two places, but if you take that chord and change it from a segment to a line and extend it, now it's called a secant. So a secant is a line that sort of cuts off this arc. And that's what I have going on right here. This is the slope of the secant line because this line cut off this arc right here. That's why we call it a secant line. And that slope of that secant line is what we would consider our average velocity from this moment in time to this moment in time, our average velocity. However, we're really looking for the instantaneous velocity. So average velocity is great, but if I want to know the velocity at an exact moment in time, as Galileo did, what should I probably do with my secant line to get a more precise velocity? Well, to get more precise, I need to shrink back this time frame right here. I need to grab this dot right here, and I can't move it here on my video, but we would grab this dot right here and we would scoot it back so that it's closer. And maybe we'd put it there. If we put it right here, then our secant line would be like this, and it would be a more precise value, which means now this is shrinking back to here or something. Okay, well, that's great. That's better. Still not instantaneous. So I go back and say, what do we need to do to our secant line so that it would show instantaneous velocity, not average velocity? Well, for that to happen, this blue dot can't be there. That blue dot needs to be on top of the original dot. I need to scoot these together even closer to where one is on top of the other. Now, if I do that, my curve, let's see if I can erase a bunch of stuff here. What happens here, well, I'm just going to redraw it off to the side. So this nice little curve that I have, whatever's going on, to get from this point, and then my second point is going to be right on top of it. I'm going to redo that. Hang on. Sorry. No, something like that. And so let's pretend my first dot is right here, and then my second dot is going to be on top of it. And at that point, when I draw my secant line, it doesn't really cut off the arc anymore. It just touches the arc. Do you remember what that line is called? Okay, so in a circle, if you have a line that just touches the edge of it in one spot, that is called a tangent line. So that's going to be the trick to finding the instantaneous velocity. Is I'm not going to look at the secant line, I'm going to look at the tangent line. All right, so now I've drawn a picture of that. So I've moved this so that it is now a single dot. And now when I do my slope formula, let's try this again. It's going to be oops. Remember that my slope formula was f of x plus h minus the f of x all over h. That's what we wrote previously. But here's what I'm going to ask now. Tell me about h. Remember, h was the distance, the horizontal distance from x to from one point to the next point. What is that distance when we move those dots on top of each other? H is now 0. And that is problematic because I can't have 0. I can't find the slope. And that's why this became such an issue of how do we figure out this instantaneous velocity if our denominator is going to end up being 0 when we do that. Okay, any ideas? How could we approach this problem differently? My hint is down here at the bottom, is as you bring this point closer and closer and closer, this line here gets shrunk in, shrunk in, shrunk in. And tell me what h is doing. H is approaching 0 as we shrink that in. So we can't use this straight up formula. What we have to do is we have to treat this formula as a limit. And that's where limits come into play. So we're going to look at it as the limit as h approaches 0. And then we have our formula, f of x plus h minus f of x all over h. Now, are we going to be able to do direct substitution? Not the way it is, but we have all these strategies that we have been learning about limits and ways that we can find this. All right, so we sort of hit a big moment here, like an aha. Okay, now we know what's going to happen. Now we just got to do it. But I thought I'd sneak in a summary page so far, just so that you got this straight. So the average velocity is the slope of the secant line. And its formula is f of x plus h minus f of x all over h. And that's great. That's where we kind of start. And then we move into instantaneous velocity, which is not the slope of the secant line. It is the slope of the tangent line. If you need to sketch yourself a little picture, well, here, I'll just do it. Here's your secant line from here to here versus a tangent line, which is right here, instantaneous. I kind of missed that, but okay. Now, this actually has a name. Because it's treated as a limit, it has a special name, and this is what we call the derivative. So when you hear your calc friends talking about derivatives, that's what they're meaning. Okay, a derivative is notated with, you can use a little prime mark, f prime of x, like that. It can look like that. It also could look like dy over dx. And both of those are interchangeable notations. I try to use both just so that you're familiar with both. Probably use that first one more often. Okay, so now that it's a derivative, I'm going to write the formula to find that instantaneous velocity, which is the slope of the tangent line, which is the derivative. All three of those things are interchangeable phrases. I'm going to ask you to find the slope of the tangent. I'm going to ask you to find the instantaneous velocity. I'm going to ask you to find the derivative. And every time I ask you this, that's the same question. So here's how it looks. The derivative is equal to, now what's different is it's a limit. You have to have that limit in there to show the difference between this versus the average velocity. It is the limit as your h approaches 0 of f of x plus h minus f of x all over h. And that's called the difference quotient, and we'll talk about that more tomorrow, but that's what we've got. That's where we're at. Now let's go use it. Okay, so first thing we're going to do is look at this graphically, and it says estimate the derivative. Now remember, the derivative is the slope of your tangent line. So your tangent line, that slope, it's going to change. And I usually use like a pencil, but in this case on my video thing, I can use a ruler. So I'm going to use a ruler. And if you can just imagine this, the edge of my ruler is a line. It's my tangent line. And so my tangent line can just touch the function. So right there, the slope of my tangent line, that's a pretty low slope. But as I ride along, and I think of it like I'm riding along on a roller coaster, you just take that thing and you keep sliding it along, and now you can see the slope of my tangent line's a little steeper and a little steeper, and I keep going and keep going and keep going, and it's steeper and steeper. So it depends on where I want my tangent to be. So in this particular example, they say at x equals 0. So I'm back over here, and I slide my ruler or my pencil or whatever it is until I get to where I'm tangent at that dot, and I feel like about right there. All right, so now what I have to do is I have to find a couple points that look like they would cross nicely on my grid, and I think I got a couple good ones. The one that they gave me was this one right here. I'll go ahead and use it. And then I'm also going to use, I think, like this one, and then I'm going to use this one out here. That looks like a pretty good one. And I just find those 2 points, count my rise over my run. So it looks like I'm going to rise 3 and run 5. So I would say that my slope, and I'm just practicing with some notation here, which remember is the derivative. And I would say it's about 3/5. Now, we are not all going to agree. You are all going to draw our line as best we can, and then we're going to hope we're close. That's what we're going to do. Okay, let's do a fancier one over here. Again, let's practice with the slope and understanding how you don't really like cross over the function. You just kind of ride along here, ride along like a roller coaster. I'm underneath, I'm underneath, I'm underneath. But at some point, oops, I'm trying to do this. Now it's going to go kind of flat. And now I'm sort of over that curve. Now I'm over the curve, back under the curve, down here. Kind of hard to do this. Now it's coming up this way, just riding the roller coaster, just all the way around. So changes all the way through. At this problem, they want to know at x equals 1. So at x equals 1, that happens right here on the function. Okay, so let me bring my straight edge back, and let's try this one more time. We're going to ride along until my point of tangency. Oops. I don't know. Looks like about there. I'm going with that. I keep touching it, it keeps changing on me. So I'm going with that spot right there. And then I have to pick two nice clean grid line points. I feel like, now you might notice that it does cross over the function there because of as you get a fancier function going, it can cross over the function. That's okay. But when you're riding along with your straight edge, you're riding along like it's just sliding along. So I'm going to use the given ordered pair there at a 1, -1. And then I feel like this dot right here is a pretty good one. So I'm going to go with, oh, I got to move this guy right here. So then my rise and my run would be 1, 2, 3, 4, 5, 6. I'm going to rise. Well, depending on which way you're going, I guess if you read it left to right, you'd be going down 6 and then right 3. So my slope, which is my derivative, would be going down 6 over 3. That's a -2 slope. So hopefully you're close to that. You don't have to be exact, but that's what we want to do. All right, so this one is one for you to try without me showing you. See if we can agree. At x equals 3. Now, at x equals 3, looks like we are about right here. What you don't do is just draw like a slash through it. That is not tangent. Remember, you got to kind of read it left to right and just slide along that thing. Let me erase that back off of there. We don't want that in there. Oh, it's not going to let me erase it. That's bad. Uh-oh. Okay, ignore it. Oh, maybe it's there. Okay. Now, you pause the video for just a little bit here. Go draw yours in, and then come back. Press pause. All right, here's what I've got. Notice I didn't even write on this one m equals. I just want it to be commonplace now that you know when you're finding the derivative, that's what it is. It happens to be the slope. And so I ended up with a 4. Hopefully you got something close to that. Okay, so we like to do the visual so you understand what's happening, but really we want something better than an approximation. We want to find the exact derivative, that instantaneous velocity. So what we're going to do is we're going to practice with some different functions and see if we can run those through this formula we've got. All right, so try here. These are going to gradually get harder, so it is important that you show some neat and some organized work. In this example, we're finding the derivative, so let's be sure that we're showing that it's the derivative we're looking for. And the derivative is a limit, so don't forget to keep your limit in there. As h approaches 0 of f of x plus h. What that means is that you take x plus h and you put it in for x in the function. That's what, when you say f of x plus h, you put x plus h in there. So f of x plus h is going to be x plus h instead of just x minus 2. And then you're going to subtract. So now we're to this part right here. Now we're going to subtract the function itself. So it's going to be a minus. And then you have to be careful with this. I'm going to do this one time, and then in the futuristically, we're just going to do it in our head. But you have to subtract the entire function, which means that's going to end up going through and changing all of those signs. But probably good to show it like this your first time through. All right, and this is all over h. Now, every time we set this up, we think in our head we should do direct substitution, and never once will that ever work because the formula is set up to never work like that. So our goal is, like what we were doing yesterday, is clean some stuff up and hopefully it will reduce. Okay, so first thing I'm going to do is I'm going to go ahead and I'm going to take this minus sign and I'm going to distribute it through. So that's going to end up a minus x plus 2. And futuristically, that's what I'm just going to write. So now I'm hoping some things can cancel for us. So I have a positive x and a negative x. I have a -2 and a +2. Oh, and all that's left is an h over an h. Those would both, that's totally, okay, that doesn't happen usually, where everything cancels. Okay, if everything cancels, all that I have left is a 1 sitting in place of everything. And there's really no longer a limit to evaluate because there's no h left. So in the end, I just have a derivative equal to 1. Okay, that's a special situation. I tried to start with a super easy function, but sometimes the super easy functions fall into your lap a little too nicely. What I really want to do, though, is see if this makes sense in your head. Think about a graph of this function. This function that I gave you is really just a linear function. It's just a slope of 1, y-intercept of 2, or I'm sorry, -2. So it just looks something like, I don't know, this. Now, if you think about drawing your tangent line to that, wouldn't it seem like your tangent line would end up falling right on top of the existing line if you were trying to slide it along that? And so wouldn't your tangent line have the exact same slope as the existing line? And what is the slope of this existing line? It's 1. That's where that's coming from. All right, let's try a fancier one. This one's going to be a quadratic. Still not super hard. It's just a straight up parent graph parabola. Here we go. Start off. We're looking for the derivative, and the derivative is the limit as h approaches 0. And then what we've got here is x plus h squared. Okay, so in class, I'm going to go ahead and do it here too, but we have got to be able to square a binomial in our head. So this x plus h that I'm going to plug in to the function right here and square it. I got to be able to do that without writing it twice and foiling it, because this is such a baby step to a much bigger problem we're going to come across that we want to be able to do this in our head. Some of you maybe already do. I'm going to do a quick, and maybe you can fast forward a minute here if you already do this, or maybe it's a good refresher. If I give you x plus 5 and ask you to square it, don't write this in your notes. X plus 5 times x plus 5. First gets you x squared. Your outer is 5x, but so is your inner. That happens every time. The outer and inner are the same thing every time. And then the last is going to end up at 25. So we're left with x squared plus 10x plus 25. I need you to be able to go from here to here. So let's see where that's all coming from. The x squared is just your first term squared. This 10x is because you ended up multiplying these two together, but then it's always there twice. So then you always have to double it. And then your last term is always this one squared. Let's see if I can do a fancier one for you to do. Let's do 2x minus 3 squared. Okay, so if you square the first term, you'd have 4x squared. Multiply the 2, that'd be a -6x, but you have to double it because it's there twice, so -12x. And then your last term is always that number, that last number squared, so it'd be a +9. Okay, so being able to do that in our head's important. So now let's do the one we really want, which is this one right here. Can we square that in our head? Sure. Square the first term, multiply the 2, that's xh, and double it. So that's a +2xh. Square the last term, h squared. All right, so now that's the f of x plus h minus the function itself, which is just x squared. So then minus x squared all over h. Can't do the direct substitution. Start looking for some things that will reduce. looks like we've got a positive x squared and a negative x squared. Okay, and nothing else cancels. But think about what I'm doing here is I'm dividing this whole numerator by h. So if I can manage to get it to where each term has an h that could be divided. So if I divide this term by h, because each term has to get divided. So this I could divide by h. Those h's could cancel, and I would just have a 2x. And an h squared and an h can cancel also. An h squared over an h would just reduce to an h. So that's sort of your goal, to get everything up here to end up with an h that you can divide out. So I think where I'm left here, can't do this. Boom. Got it. The derivative is going to be the limit as h approaches 0. And dividing everything by h and the things that are canceled, I'm going to end up with a 2x plus an h. All right. What I managed right there was to get rid of that denominator. So now I'm going to be able to do my direct substitution. Now I'm going to plug that 0 in for h. If I plug 0 in for h, I'm just going to have a 2x. So the derivative is equal to 2x. Now, is this the first time we've gotten a derivative that's not really a number? Okay, that's okay. We want this to make sense. Let's talk about why that's the case. Here's what I've got. I've got a parent graph parabola. It just looks like this. But the slope of the tangent line is going to change depending on where I'm at on my x-axis. If I'm over here at x equals -1, here's the slope of my tangent line. And at -1, okay, so my slope is going to end up negative there, okay? But if my slope, or if I was over here at 3, let's say x is equal to 3, now your slope is going to be more of a positive, a little bit steeper looking. So it's okay for your derivative to end up being a function. That just means the derivative will change depending on what x value you're using. All right, last one. Definitely fancier. All right, I've got a 3x squared plus 1. Now, this actually says find the derivative at a particular point. So this time, I want to find the derivative because I think it's going to change. It's another parabola. It's going to change. So I'm going to look specifically at a spot at x equals 2. Now, I'm really going to ignore that until the very end. I'm going to still do my formula the same way we've been doing. But it's a more difficult function. I'm going to do a 3x squared plus 1. Okay, so I have to take x plus h, and I have to put it in right here. I have to square that x plus h, and then I have to multiply it by 3. All right. So, side note, x plus h squared times 3. Well, we would square the first term. It would look like this. Multiply the 2 and double it, 2xh, and then square the last term. But now you're going to take all of those times 3. Now, again, kind of would like you to be able to do the squaring and the times 3 all in one shot. So if you've been using this shortcut forever, this is going to be easy peasy. If not, we kind of need to be getting you able to do that mental math so that we can be doing more complicated problems. So what I'm going to end up with is a 3x squared plus a 6xh plus a 3h squared. But we have to finish the function. It's 3x squared plus 1. So I still have to do the plus 1 at the end of that. Okay, so that, what I just did, is f of x plus h. Now I have to subtract the function. So that means subtracting the entire function. Remember how we have to distribute the minus to all the parts of the function. So it's going to end up being a minus 3x squared and then a minus 1. And this is all over h. All right, a lot more going on here. but still the process is the same. You start looking for things that you can reduce. What do you see that we could cancel out? 3x squareds, ones. Okay, I think that's it on this. Now remember, our hope is that everything that's left has an h that you could reduce it by. And we do. Everything has an h. There's only 2 terms there. Okay, this is going to be great. Here we go. Oh, I keep doing that. The reduced version would end up being just a 6x plus a 3h. Once you have this simplified and this this denominator of an h is gone, now you're going to do your direct substitution, which is what we've been doing with our limits the past couple days. You plug your 0 in for your h. That's going to make this go away, and my derivative is simply 6x. Okay, now remember, if they're just asking for the derivative, you're done. But this particular problem was asking for the derivative of the function at x equals 2. So that means once you get to this stage, you go one step further, and you're going to say, all right, so the derivative of 2, or at 2, and you just plug 2 in for your x, would equal 12. So you just do that one more step at the end. Okay, now I said this was the last one. Well, this is the last function. I'm going to practice this derivative process with you, but I'm going to go a step further on this. It says we found the derivative at that point. I'm going to ask for one more thing. I would actually like to have the equation of that tangent line at x equals 2. So let's think about what that would look like. The function I gave you was a 3x squared, so that's a parabola, skinny parabola, plus 1. So it went up 1. So here's what I've got, something like this. And then I looked at when x was equal to 2. So I don't know, somewhere right here. So the tangent line I'm dealing with is like this one. Oh, remember the answer we got? We said that the slope was 12. Well, we said the derivative was 12. Look at my line. It's a pretty darn steep line. So 12 sort of makes sense. Now, not going to be perfect, but I like the idea that it's pretty darn steep, had a pretty large slope. Now, what I'm looking to do here is write the equation of this red tangent line. So we're in Algebra 1. Write the equation of a line. What kinds of things do we need? We'd like the slope. We know the slope. The slope is 12. We found it on the previous slide. Okay. How about a point? Could you tell me a point? Well, the point we want is probably the point of tangency there, because you know that the x value on that point is 2. But how do you find the y value on that point? Well, you're just going to plug 2 back into the original function to see what its matching y value is. Here's what this would look like. You would write f of 2. This x value goes in here. Notice this is not the derivative, it's just the original function. So it's going to be 3, 2 squared plus 1. So that's a 4, 12 plus 1, that's a 13. Okay, so the point then that we want is 2, 13. So between this and this, we can write the equation of our line. Typically, we're going to go ahead. I'm going to just change colors just because it might start getting cluttery looking here. So I'm going to do y minus y equals m x minus x. Distribute the 12. Add the 13. and you get a, oops, get a negative 11. Okay, so ideally, this should match what you have going over here. So does it look like I have a slope of 12? Kinda, yeah, I thought so. Does it look like my y-intercept down here is at negative 11? Well, I don't know. Maybe not exactly, but I can see that it would be way down there. And so if I actually had a grid there that I was graphing that on, I'd feel more comfortable with that. And so on your homework, that's what you're going to have. You're going to have some problems where, and if you were in class, we did some of them together, but I do different parts of this whole lesson, but there is a part where you kind of are doing all of this stuff in one shot. You have to sketch me a graph. You have to find the derivative. You have to find the slope of the tangent line at a particular spot. So you can use that to write the equation of the big picture. All right, so not the whole assignment, but it's a pretty big one. So go watch the video again if you need to on some parts. You should have a worksheet for your homework tonight, day 3. All right, have a great night. Bye.